Now we're going to go back to particle kinematics. And since we'll be talking about accelerations as part of kinematics, um, you can imagine how this relates to particle kinetics. Through Newton's laws, acceleration comes into calculations of forces and things. But we're going to go back to it in a case that comes up a lot in dynamics, and that is when your coordinate system is rotating. In other words, the orientations of the coordinate axes are not constant. So now we're going to talk about particle kinematics in a rotating coordinate system. At the beginning of the term, I gave an example on the board of that crazy astronaut contraption that spins around on a long, the person's in a chair on the end of a long arm. It builds up a lot of centripetal acceleration. And so it's a way to measure a person's ability to deal with high G accelerations. And I'll talk about how that relates again here in a minute. But before I do that, remember this: in a non-rotating coordinate system, if you have a vector u and you take the time derivative of it, you have like what you get is just the time derivatives of the components. That was part of, you had practice problems like that at the beginning when we first talked about particle kinematics. Another way to write that is u dot is equal to ux dot times the unit vector in the direction of x plus uy dot times the unit vector in the direction of y plus uz dot times the unit vector in the direction of z. Okay, this isn't true anymore in a rotating coordinate system. So why is that? It's because in a rotating coordinate system, well, actually, let me say it like this. U dot, if we think about, so u is equal to ux times I plus uy times j plus uz times k. And so using the product rule, u dot has to be equal to ux dot times I plus ux times I dot. And derivative of that second term is uy dot times j plus uy times j dot. And the derivative of the k term, uz dot times k plus uz times k dot. And so these things, this is what's different in the rotating and non-rotating coordinate system case. In a non-rotating coordinate system, these three terms in red boxes are all equal to 0 because the orientations of the coordinate axes aren't changing in time. So the time derivatives are 0. And all we're left with are the components dotted, and that's what you see up here. In a rotating coordinate system, these are not non-zero. They are something. And that is because over time, the orientations of these axes are changing. And so the question is, the tricky thing to make sense out of when you deal with rotating coordinate systems is what are these, or I guess what is this? Ux times I dot plus Uy times J dot plus Uz times K dot. It turns out that it is a pretty simple expression that this is equal to, and even proving it is not that tricky. Like you could follow the proof in 2 dimensions. It's more complicated in 3 dimensions, but you could easily find that online or come talk to me if you're curious about it. But I'm just going to skip over that and go straight to the result. So our first big result for rotating coordinate systems is that Ux I dot plus Uy J dot plus Uz K dot is equal to capital omega crossed with U where this capital omega is the angular velocity of your rotating coordinate system with respect to a non-rotating coordinate system. And notice how general this result is. This says that no matter what your vector is, no matter what that vector is measuring, if you want to take the time derivative of that vector, you're going to have this correction term that's equal to the angular velocity of your rotating coordinate system crossed with that vector. This doesn't have anything to do necessarily with kinematics yet or anything like that. So how does that relate to kinematics? Well, remember that the problem in doing kinematics in a rotating coordinate system comes about when you take the derivative of the position vector and, well, okay, I'm getting ahead of myself. Let me say one more thing before I go into that. So therefore, for any vector u expressed in a rotating coordinate system, that vector dot is equal to the time derivative of the components plus the angular velocity of the rotating coordinate system crossed with that vector. Okay, that's the result that we're going to use in kinematics. And you can think of this term here as like a correction term, okay? That's the term that you add on to deal with the fact that your time derivatives are messed up because you're in this rotating coordinate system. Okay, so now we're going to apply this to kinematics. The position vector doesn't need any correction because you're not taking any time derivatives to get that. But to go from position to velocity, you need to take a time derivative. And so we're going to apply this rule, and you get, so for a velocity vector, we know that that's equal to the time derivative of position, and that time derivative is the time derivatives of the components plus the angular velocity of the rotating coordinate system relative to a non-rotating one, crossed with the position vector. And now, what do you think to calculate the acceleration? Well, we're going to do the exact same thing, except now we're going to start with this more complicated thing where we have this correction term. So we're going to have to take derivatives of a bunch of things and use the product rule. So the acceleration, let me move to the next page. So for acceleration, we know that A is equal to V dot. We just calculated V dot, so we're just going to use that derivative rule on the velocity that we just established. And using the product rule, we get first, second time derivatives of all those position components. Plus omega crossed with the time derivatives of all the position components. Plus the time derivative of that angular velocity. You can think of that as like the angular acceleration of the coordinate system relative to a non-rotating coordinate system. Plus angular velocity of the coordinate system crossed with the time derivatives of the components of the position. Plus omega cross p. And you can simplify this, group like terms together, and you get that the acceleration vector is equal to px double dot, py double dot, pz double dot, plus that angular acceleration of the coordinate system crossed with the position vector, plus 2 times omega crossed with the position components dotted, plus omega cross quantity omega cross position. So that's an expression for the acceleration that corrects for all the things that happen in a rotating coordinate system. And in this case, what's the correction term? Well, you know that in a non-rotating coordinate system, the acceleration is just the time derivatives of the components. So all of this other stuff is, comes about because of the rotation of the coordinate system. Everything else is a correction. Okay, one thing that you should keep in mind is really the big important result here was how you take time derivatives of vectors in rotating coordinate systems. Once we accepted that, deriving the velocity and acceleration equations, the expressions for velocity and acceleration was easy. And so I would recommend getting used to deriving these from that general time derivative. Okay, so let me go back to that astronaut chair, possibly fictitious device, um, and I'm going to use it to show why you have to do this. And we'll put some numbers to it. And I'm going to do it in a little bit different way than I did at the beginning. But this will show how to use this equation and how this equation gives you accelerations that make sense. So this is a conceptual example. Okay, so there's the axis of rotation, and here's the astronaut wannabe, finding out if he has enough resistance to G-forces to be an astronaut. He doesn't have a neck. I don't know if that's going to be a problem with his training. Okay, and let's say that the mass, am I going to use that? Actually, no, I'm not going to use the mass, so I'll just leave that off. And let's say that we have a coordinate system like this, x, y, and z, and that this thing is spinning around at 2 radians per second. And say that the coordinate system is rotating with this chair. The question is, what's the acceleration vector of the astronaut that we could use in Newton's second law to calculate forces and things like that? And let's say that this distance is 5 meters. So let's think about what would, so remember to think about this coordinate system as a camera. If you had a camera mounted on this coordinate system, rotating around with the astronaut, what would this camera see as it looked at the astronaut? And we're going to use that to have an idea to think about the meaning of the position vector as a function of time. Okay, so here's the view of the camera. Okay, it's looking down the, let's look back at this for a second. It's looking in the negative x direction at the astronaut. And so it would see the z-axis pointing this way, the y-axis pointing this way, and the positive x-axis pointing out. And the whole time it was looking, here's what it would see. It would see the astronaut sitting there. And, you know, the astronaut might be moving around, shuffling around in his seat, but essentially this camera is just going to see a stationary object that's in the negative x direction. And so as a function of time, the position is 5 meters in the negative x direction, 0, 0. Okay. All right, so based on that, if we didn't know that the coordinate system was rotating, we would take the time derivative and I'm going to call these the apparent velocity vector, which is just the time derivatives of the components. Is 0, 0, 0. That makes sense because looking at him, all we see is just a stationary thing. And the apparent acceleration is just the second derivatives of these position components. And that's equal to 0, 0, 0. Okay. And what's the problem here? Well, the problem is, say that we had force sensors mounted in the chair, and we were actually measuring the forces that were being applied to the astronaut by the chair. They'd be reading big forces because that chair would have to apply big forces to keep him spinning in that circle. But compared to our acceleration values, it wouldn't appear to satisfy Newton's second law. Okay, and so that's where those correction terms come into play. We're going to come up with a way, or we did come up with a way, to calculate the acceleration so that we can use it with Newton's second law and it will make sense. So instead, we're going to use that the acceleration is equal to the second derivative of the components plus the angular acceleration of the coordinate system crossed with the position vector plus 2 times the angular velocity of the coordinate system times the time derivatives of the position components plus omega cross the position vector. For us, in the example that I gave, our apparent acceleration is this, the second derivatives, and we already know that that's all equal to 0. We're talking about a constant angular velocity, so we have 0 vector times p, so that's going to be equal to 0 also. And then we have 2 times the angular velocity of this rotating coordinate system is 0, 2, 0. The first time derivatives of the position vector is 0, 0, 0, so that goes away again. And then finally, we have 0, 2, 0 crossed with the quantity 0, 2, 0 cross negative 5, 0, 0. The only thing that doesn't go away is this term. And if you do that calculation, you get 20 meters per second squared, 0, 0, or a little over 2 Gs. And what we have here is the centripetal acceleration that we would expect that went away when we were just looking at the apparent acceleration viewed by that rotating coordinate system. Okay, so there are a few things I want you to notice about this. First, notice that Px, Py, and Pz dot is the observed or apparent velocity vector And the second derivatives is the observed or the apparent acceleration vector. The correction term omega dot crossed with the position vector is an unobserved, and by unobserved I mean unobserved in the rotating coordinate system, to an observer who's fixed to the rotating coordinate system, who's rotating with it. This is a correction term associated with tangential acceleration. Third, omega cross quantity omega cross p is, again, to a viewer who's rotating with that coordinate system. This is an unobserved centripetal acceleration. And then last is the term 2 times omega cross with the observed velocity or the apparent velocity, which is the components dotted. And I'm just going to say this is a weird, unobserved thing. And it's actually given a name. It's called the Coriolis acceleration. And we're not going to go much into, I guess I would say we're not going to go at all into what this acceleration is, what this term appears, how this term appears to observers in a rotating coordinate system. But there are resources online. You can watch videos and things like that if you're curious about it. Otherwise, I think it's just important to know that name because that name comes up from time to time. So now what we're going to do in the next lesson is just talk about some applications of these correction terms and doing these calculations of velocities and accelerations when your coordinate system is rotating.